Welcome to this deep dive. We're really getting into the universe today based on this fantastic stack of source material you've provided.
Yeah, it's quite a collection. It takes us from, our closest cosmic neighbors right out to the very edge of what we think we know.
Exactly. So we'll be exploring planets, stars, galaxies, um, even how we figured all this stuff out, and some pretty remarkable people involved too.
It's a great journey laid out in your sources, less about just listing facts, more about grasping the sheer scale of it all and the story of our understanding.
Okay, so our mission here is to unpack that, pull out the key ideas, the things that make you kind of look up at the sky a bit differently. We're starting close to home, then heading out.
Sounds good. Let's kick things off right here in what you might call our cosmic backyard. The sun, the earth, and the moon.
Right. And you really have to start with the sun, don't you? Your sources describe it as our closest star, the absolute center of things for us.
It is, and it's just this immense ball of churning, super hot gas. We're talking like 10,000 degrees on the surface. And that constant stream of light and heat it pours out, that's what makes life here possible. It powers everything.
It's funny, for ages, it really looked like the sun went around us. You see it rise, you see it set.
Oh, absolutely. That was the common sense view based on what you see every day. But one of the biggest breakthroughs, which your material highlights, was realizing it's the other way around.
It's us going around the sun.
Exactly. Earth orbits the sun.
And that orbit defines our year, right?
Yeah.
Takes about 365 days for one full trip.
That's our year. And at the same time, we're also spinning like a top.
On axis.
Mm-hmm. One full spin takes about 24 hours. That's our day. And that spin is why we have day and night as different parts of Earth face the sun.
Okay, but here's the really clever bit your sources get into. Why isn't it just warm or cold all year round? The seasons.
Ah, yes. That's down to Earth's tilt. The axis we spin on, it isn't perfectly upright compared to our orbit. It's tilted slightly.
And that tilt makes all the difference.
It's everything for seasons. When your part of the Earth is tilted towards the sunlight hits more directly. It's more concentrated. That's summer.
Okay.
When you're tilted away, the sunlight comes in at more of an angle, spreads out more, less intense heat. That's winter.
Which is why the seasons are opposite in the northern and southern hemispheres.
Yeah,
It all clicks into place because of that tilt.
precisely. It's quite an elegant system.
So this whole setup, sun, earth, moon, all the other planets orbiting, that's our solar system. And solar comes from sol, Latin for sun. Makes sense.
It does. Now, orbiting us is our closest companion, the moon. Your sources describe it simply as a rocky ball.
And it takes about a month to go around Earth. But crucially, it doesn't make its own light, does it?
No, not at all. It's basically a giant mirror reflecting sunlight.
So those phases of the moon, we see crescent, half full moon.
That's just us seeing different amounts of the sunlit side as the moon travels around us. The moon itself isn't changing shape. It's just our viewpoint changing.
And sometimes, everything lines up just perfectly for eclipses.
Right. Your sources covered the two main kinds. You get a solar eclipse when the moon passes directly between the sun and Earth.
Blocking the sun.
Exactly. It casts a shadow on Earth. It can be pretty dramatic, a total solar eclipse. But the sources rightly warn, never, ever look directly at the sun during one. Even a sliver can damage your eyes permanently.
Seriously important safety tip, okay? And the other kind, lunar.
A lunar eclipse is when Earth gets between the sun and the moon. So Earth's shadow falls onto the moon, making it look dim or even reddish.
Are they equally common?
Well, lunar eclipses are actually seen much more often from any given place on Earth. Total solar eclipses are rarer for a specific location because the moon's shadow is quite small.
Got it. Okay, so beyond the Earth and moon, we've got the rest of the planets. Your sources list the 8. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune.
And they fall into sort of two groups. The first 4, Mercury, Venus, Earth, Mars, are the inner planets. They're smaller, rocky, with solid surfaces.
And they orbit the sun much faster, being closer. Like Mercury whips around in just 88 days.
Yeah, compared to Earth's 365. And then you look way out at Neptune. It takes 165 Earth years for it to go around once.
Whoa. That really gives you a sense of the scale, doesn't it?
It absolutely does. So looking at those inner ones, Mercury's the smallest, closest in, named after the speedy Roman messenger god, fittingly. It gets incredibly hot on the sun-facing side and freezing cold on the night side. Wild swings.
Then Venus,
Yeah.
named for the goddess of love. similar size to Earth, I think.
Roughly, yeah. And it's covered in clouds, so for a while people wondered if it might be, Earth-like under there.
But it's really not.
Not even close. Your sources make that clear. It's got this crushing atmosphere and is unbelievably hot, hotter even than Mercury sometimes, due to a runaway greenhouse effect.
Crazy.
Definitely no place for life as we know it. A good lesson in not judging a book by its cover or a planet by its size.
Right. Okay, then there's Mars, the red planet, named for the god of war. That red color comes from rust, essentially.
Yeah, iron oxide in the rocks and dust. And Mars is, well, it's where a lot of the life elsewhere discussion focuses in our solar system.
Because we've sent probes, rovers.
Exactly. And they've found evidence of water ice. Your sources mention this sparks debate. Is it too cold and dry now for life? Maybe. But could life have existed there billions of years ago when it was warmer and wetter?
Or could it still be there, like underground?
That's another possibility some scientists are exploring. Life hiding beneath the surface, protected from the harsh conditions. It shows how finding just one thing, like ice, can lead to big questions and different scientific ideas.
Fascinating. Okay, moving further out now past Mars.
We cross the asteroid belt, we'll come back to that and reach the giant planets. First up is Jupiter.
The biggest one, by far.
Huge! And your sources mention its incredible collection of moons. Over 63 are known now, and some of them are actually bigger than our own moon, even bigger than Mercury. It's like a mini solar system itself.
And then Saturn. You can't miss Saturn. The rings.
Those spectacular rings. Your sources explain they're not solid. They're made up of countless bits of ice and dust, all orbiting the planet, reflecting sunlight. Just beautiful. And Saturn also has a ton of moons.
After Saturn.
We get to the outer giants, Uranus and Neptune. They're way out there. Very cold, kind of icy giants.
They have rings, too.
They do, yes, but they're much fainter and harder to see than Saturn's. And they both have moons as well. Neptune's so far away you definitely need a telescope. Uranus is just maybe barely visible to the naked eye if you know exactly where to look, and conditions are perfect.
And your sources mention Pluto. The odd one out now.
Yeah, for a long time it was planet number 9. But then, around 2006, astronomers found other objects out there similar in size to Pluto. It forced them to sort of rethink the definition of planet.
So Pluto got reclassified.
As a dwarf planet. It's a good example of how science isn't static. Definitions change as we learn more.
Right. Okay, so it's not just planets out there orbiting the sun. There's other stuff, too.
Loads of it. Millions of asteroids, for starters. These are chunks of rock, metal, sometimes ice. Most of them hang out in the asteroid belt between Mars and Jupiter.
But not all of them.
No, some have orbits that bring them closer to the sun or take them further out.
And then there are comets. Those are different, right? More icy.
Yeah, think of them as dirty snowballs, mostly ice and dust. When their orbit brings them near the sun, the heat starts to vaporize the ice.
Creating that tail we see.
Exactly. The sun's radiation and solar wind push the gas and dust away, forming that characteristic glowing tail, which always points away from the sun.
Halley's Comet is the famous one. Shows up every 76 years.
That's the one. Last seen in 1986, a predictable visitor, which is pretty cool.
What about smaller bits?
Smaller space rocks are called meteoroids, just drifting around.
Until they hit our atmosphere.
Right. When a meteoroid plunges into Earth's atmosphere, friction makes it burn up incredibly brightly. That flash of light is what we call a meteor.
A shooting star.
That's the popular name, yeah. And when you see lots of them at once, perhaps because Earth is passing through a trail of debris left by a comet, that's a meteor shower.
Do any of them ever make it through?
Some do. If a piece is large enough to survive the fiery plunge and actually land on Earth, we call that piece a meteorite.
And they can make quite an impact. Your sources mention meteor crater in Arizona.
A huge hole in the ground. Your sources show pictures comparing it to roads and buildings nearby, and it just dwarfs them. A powerful reminder that things from space do hit us sometimes.
Okay, so we've toured the solar system. But even this whole system is just tiny in the grand scheme of things.
Incredibly tiny. Let's zoom way out now to stars and galaxies. Your sources remind us our sun. It's just one star.
One among trillions.
Exactly. All those little points of light you see in the night sky, most of those are other suns, other stars. They look small and dim simply because they are unbelievably far away.
But they're basically the same kind of thing. Balls of hot gas.
Fundamentally, yes. Balls of hot gas generating light and heat through nuclear fusion. But astronomers, the scientists who study stars, the name comes from astron for star, see huge variety. Stars differ enormously in size, color, temperature, brightness, and of course distance from us. Generally, hotter stars look whiter or bluer, cooler ones look redder, and being closer makes a star appear brighter to us, naturally.
And stars aren't just scattered randomly, are they? They come in groups.
Massive groups. That's one of the biggest realizations your sources talk about. Stars are clustered together by gravity into absolutely enormous structures called galaxies.
And when you say enormous,
We're talking billions of stars in a single galaxy. Billions. Along with vast clouds of gas and dust, all held together by gravity.
our own galaxy is the Milky Way.
That's right. Our sun, our entire solar system, is located within the Milky Way galaxy. It's shaped like a spiral, though we can't see that shape from inside it.
From Earth, it just looks like that faint, hazy band across the sky, the Milky part.
Exactly. That's us looking through the flat disk of our own galaxy.
Is Andromeda the closest other big galaxy?
It's the nearest large spiral galaxy to us, yeah?
Yeah.
Still incredibly far away, billions upon billions of miles, but it's so big you can sometimes just spot it as a faint fuzzy patch in the sky on a clear, dark night. And it also contains billions of stars.
So stepping back even further,
Yeah.
the universe. What is that then?
The universe is everything. All the galaxies, all the stars within them, all the space in between, all the matter and energy. And your sources emphasize the scale again. Scientists estimate there are billions of galaxies out there.
Billions of galaxies, each with billions of stars.
Yeah.
The numbers are just staggering.
It's almost impossible to truly wrap your head around the sheer vastness.
With all those stars up there, it's pretty amazing that people for thousands of years have managed to find patterns to make sense of it.
It really is. Even though we can only see maybe 2,000 stars with the naked eye from any one spot, ancient cultures all over the world looked up and saw shapes, told stories.
We connected the dots.
Literally. They grouped stars into patterns we call constellations. Your sources mention Ptolemy, an ancient astronomer who described 48 of them shapes like a bull, a crab, a bear. He was mapping the sky based on the brightest stars.
And today, we recognize more.
Modern astronomy officially lists 88 constellations covering the entire sky.
Your sources give Ursa Major, the Great Bear, as an example.
A very well-known one in the northern hemisphere.
Mm.
And part of Ursa Major is an even more famous pattern, or asterism, the Big Dipper. Those 7 bright stars making a sort of scoop shape.
And there's a Little Dipper, too, and Ursa Minor, the Little Bear.
That's right, another pattern of 7 stars. And the really important star in the Little Dipper is the one at the very end of its handle.
Polaris, the North Star.
The legendary North Star. What makes it special, as your sources explain, is its position. It happens to be almost directly above the Earth's North Pole.
So as the Earth spins,
Polaris appears to stay fixed in the northern sky while all the other stars seem to circle around it.
which makes it incredibly useful for navigation. Find Polaris, and you know which way is north.
For centuries, sailors and travelers relied on it. And your sources mention a neat trick. You can use the 2 stars at the end of the Big Dipper's bowl, the pointer stars. They point almost directly towards Polaris. It's a great example of finding practical use in those celestial patterns.
Seeing patterns was one thing, but really exploring space required tools. We couldn't just rely on our eyes forever.
Absolutely not. For millennia, that's all we had. But the game changer, highlighted in your material, was the telescope. And Galileo using one back in 1609.
Even his first one was pretty basic, only 3x magnification.
Tiny by today's standards. But it was enough. He pointed it upwards and saw things nobody had clearly seen before. Moons orbiting Jupiter, the phases of Venus, mountains on the moon, and that the Milky Way was actually made of countless individual stars. It opened up the universe.
And telescopes since then have just gotten bigger and better, placed high up on mountains.
In observatories, yeah. To get clearer views above the thickest, most turbulent parts of the atmosphere.
Or even better, put them in space, like Hubble.
The Hubble Space Telescope. Launched by NASA, the U.S. Space Agency, in 1990. Orbiting above the atmosphere entirely, it's given us unbelievably sharp images and incredible data. Your sources credit Hubble with helping nail down the age of the universe to around 13 or 14 billion years. Just revolutionary.
Okay, so we got better at looking, but then came the challenge of actually going there. Sending humans, that must have seemed impossible.
It was a huge leap, and there were real concerns about whether humans could even survive in space. Your sources mentioned NASA actually sent apes first.
To see the effects on primates.
Yeah, to study how spaceflight affects beings physiologically similar to us. The first American human in space was Alan Shepard back in 1961, but it was a very short up-and-down flight, not even a full orbit.
The really big one, detailed in your material, was Apollo 11, landing on the moon in 1969.
The moonshot. To even get off Earth, you need tremendous power to fight gravity. That's what those giant rockets like the Saturn V for Apollo were all about, brute force.
And Apollo 11 had 3 astronauts.
Right. Michael Collins stayed in orbit around the moon in the command module Columbia. Neil Armstrong and Buzz Aldrin went down to the surface in the lunar module the Eagle.
Armstrong flew the landing.
Piloted it down manually for the last bit, finding a safe spot. And then he stepped out. That iconic moment, that's one small step for man, one giant leap for mankind. Aldrin followed him out soon after.
And they needed those bulky spacesuits. Because the moon has no air.
No air, extreme temperatures, boiling hot in sunlight, freezing cold in shadow. The suits were like personal spacecraft, providing oxygen, pressure, temperature control, essential for survival. After their moonwalk, collecting samples, planting the flag, they blasted off in the top part of the Eagle, met up with Collins in Columbia, and headed home. Splashed down in the Pacific Ocean, picked up by a ship, an absolutely incredible achievement.
It really makes you wonder, what's it like up there, being off Earth? Your sources give some clues about life in space.
The biggest, most immediate difference is gravity, or the lack of it, relatively speaking. Earth's pull is strong. The moon's is much weaker, about 1/6. That's why the Apollo astronauts could take those big bounding steps.
And in orbit, like on the space station?
You're constantly falling around the Earth, so you experience effective weightlessness. That's the floating we always see.
Which looks fun, doing flips easily.
It probably is. But it has downsides. Your sources mention, let go of your food, and it just floats away. Everything has to be managed carefully.
And the environment itself is hostile. No air,
Yeah.
so you need tanks or a sealed spacecraft.
No air also means no sound travels. Silent space. And it's incredibly cold out in the vacuum.
So day-to-day living must be completely different. You mentioned exercise.
Crucial. Just floating around doesn't work your muscles or bones, so astronauts have to exercise regularly, often strapped to treadmills or resistance machines, to prevent losing muscle mass and bone density.
And simple things like washing.
Become complicated. Your sources describe showering in space. You're in a special pod, you spray water, but it just clumps and sticks to you because of surface tension. You have to sort of squeegee it off, and there's a vacuum system to suck away the droplets so they don't float into equipment.
Eating must be weird, too, with everything wanting to float away.
Food often comes in paste form or in packages designed to minimize crumbs. And sleeping. You can do it anywhere, in any orientation. Often astronauts strap themselves in sleeping bags attached to a wall so they don't drift around and bump into things.
Coming back to Earth after months of that must be a real shock.
A huge adjustment. Your sources say astronauts describe feeling incredibly heavy when they return. Their muscles have weakened, their sense of balance is off. It can take weeks to fully readapt to Earth's gravity.
And some even miss space.
Apparently so. Some report feeling almost homesick for the freedom of floating after being back on Earth for a while. It's a unique perspective.
After Apollo, landing people on the moon, what came next? The sources mention a shift towards reusability.
Right. The Apollo rockets were incredible, but also incredibly expensive and used only once. For more routine access to space, something else was needed.
Enter the space shuttle.
Exactly. The Space Shuttle program ran from 1981 up to 2011. The idea was a reusable vehicle. It launched like a rocket with large booster rockets and an external fuel tank.
But it landed like an airplane.
Landed on a runway, yeah. So the orbiter itself could be refurbished and flown again. It wasn't fully reusable. The boosters were recovered and the tank was discarded, but it was a step in that direction.
And what did the shuttles do?
A whole range of things. They carried astronauts and satellites into orbit, deployed probes, acted as a laboratory for experiments, especially studying weightlessness, and, crucially, they were essential for building the International Space Station.
They ferried up the big modules, supplies, crew.
They were the workhorses for ISS construction and servicing for many years, right up until the program ended in 2011.
So what's NASA focusing on now, post-shuttle?
Your sources mention a mix of things. Continued use of unmanned probes and satellites for exploration and science, studies focused on the moon, possibly using it as a stepping stone, and even looking at missions to asteroids.
And the International Space Station is still...
Oh yes, the ISS. A truly amazing example of global cooperation. The US, Russia, Europe, Japan, Canada, all working together. It orbits Earth continuously.
And astronauts live up there for months at a time.
Typically, crews stay for about 6 months. It can house usually 3 to 7 astronauts, sometimes more during crew changes. It's a permanent orbiting laboratory.
And life on the ISS is Well, just like we discussed.
Right.
Floating, exercise, tricky showers.
Exactly. All those aspects of living in microgravity apply there every day. It's our main outpost for learning how humans adapt to long-duration spaceflight and for doing science you just can't do on Earth.
You know, hearing about all this exploration, it really highlights the people involved, the engineers, the scientists, the astronauts themselves. Your sources spotlight a couple of really key figures.
They do. Dr. Mae Jemison is presented as a fantastic example, a real role model.
Her background is just incredible. Doctor, engineer, scientist, astronaut.
Yeah, she excelled academically, finished high school early, went to Stanford for chemical engineering and African American studies, then medical school, then she volunteered for the Peace Corps in West Africa, working on healthcare. Just amazing drive.
And then she decided to become an astronaut.
Applied to NASA, didn't get in the first time, but tried again, and was selected from something like 2,000 applicants, went through all the intense training.
And made history in 1992.
On the Space Shuttle Endeavour. She became the first African-American woman in space. She conducted experiments on motion sickness and bone cells in weightlessness, a successful mission on all fronts.
And she didn't stop there after leaving NASA.
No, became a professor, started her own company, focused on using technology to help people, especially in developing nations. Her story really shows how diverse talents and a commitment to making a difference can lead to incredible things.
The other figure your sources focus on takes us way back in time. Nicholas Copernicus.
A true revolutionary thinker from centuries ago, a scholar in many fields, math, astronomy, medicine, law.
And he challenged a view that had held for, well, forever.
For over 1,400 years, the idea that Earth was the fixed center of everything and the sun, moon, planets, stars all revolved around us, the geocentric model.
It seems obvious now, but back then.
It matched observations. The sun appears to move across the sky. But Copernicus, through careful observation without a telescope, mind you, maybe from a tower and especially through mathematics, came to a different conclusion.
That the Earth moves.
Yes. He proposed the heliocentric model. The sun is at the center, and Earth is just another planet orbiting it. And that the Earth rotates on its axis once a day, which is why the sun and stars appear to move across our sky.
That must have been controversial.
Hugely. It went against common sense, against the established scientific view derived from ancient Greek philosophers, and against the teachings of the church at the time, which placed Earth and humanity at the center.
So his ideas weren't immediately accepted.
Not widely, no, not in his lifetime. People like Galileo later supported his ideas, using telescope observations as evidence, and faced serious opposition, even punishment.
But Copernicus was right.
He was! And your sources highlight the courage it took to propose something so radically different based on careful reasoning and observation. It's a powerful example of how scientific understanding isn't fixed. It changes, it evolves based on evidence, even if it takes time to be accepted.
Which sort of leads us to the biggest question of all, one your sources tackle right at the end. How did this whole universe even begin?
The ultimate origin question. Ancient myths and religions offered explanations, of course. But modern science looks for answers based on observation and evidence.
And a key piece of evidence came from Edwin Hubble. We mentioned the telescope named after him.
Right. Back in 1929, Hubble made this incredible discovery. He observed that distant galaxies are all moving away from us. And not just that, but the farther away a galaxy is, the faster it seems to be moving away.
Hubble's law.
Exactly. This strongly suggested the entire universe is expanding.
Which implies, if you run the clock backwards,
everything must have been much closer together in the past, denser, hotter. This observation is the bedrock of the prevailing scientific explanation, the Big Bang Theory.
Now, theory here doesn't mean just a guess, right?
No, in science, a theory is a well-substantiated explanation for some aspect of the natural world, based on a body of facts that have been repeatedly confirmed through observation and experiment. So the Big Bang Theory is our best explanation, built over decades, starting in the mid-20th century by physicists and astrophysicists, building on Einstein's work too.
So what does the theory actually propose?
The core idea is that around 13.8, maybe 14 billion years ago, all the matter and energy in the observable universe was concentrated into an incredibly tiny, hot, dense state.
And then?
It began to expand rapidly. Not an explosion into space, but an expansion of space itself. That initial rapid expansion is what we call the Big Bang.
And the universe was very different back then.
Unimaginably hot and dense. No stars, no galaxies, just a sort of soup of fundamental particles. As the universe expanded, it cooled down.
Allowing things to form.
Exactly. Gravity started pulling matter together. Over hundreds of millions of years, this led to the formation of the very first stars and eventually the first galaxies.
And our own solar system,
Yeah.
sun, planets, that came much later.
Much later, formed from the remnants of earlier generations of stars, maybe around 4.5 or 4.6 billion years ago.
And this is still something scientists are actively studying.
Oh, absolutely. Your sources make that clear. We're constantly gathering new data from telescopes like Hubble and its successors, from studying cosmic background radiation left over from the early universe. The theory gets refined, updated as we learn more. It's an ongoing process of discovery.
Wow. This deep dive using your source materials, it's really taken us on quite a ride.
It really has. From things we see every day, like the sun and moon, understanding the tilt that gives us seasons,
Out through the planets, each with its own character, past asteroids and comets.
to grappling with the sheer scale of stars and galaxies. Billions upon billions. It's mind-bending.
And seeing how humans made sense of it, finding patterns like constellations, using the North Star.
Then tracing how we learned to explore it, from Galileo's first look through a telescope, to modern observatories, to the incredible feat of sending people to the moon.
And learning what it's actually like to live and work in space
Yeah.
on the ISS. The floating, the exercise, the weird showers.
And being reminded of the people behind the breakthroughs, pioneers like Copernicus challenging centuries of belief, and modern trailblazers like Dr. Mae Jemison breaking barriers. It shows that science moves forward because of curiosity and courage.
It really does.
Okay.
This whole exploration underscores the incredible complexity out there and our own determination to understand our place within it all.
So thinking about everything we've touched on, the immense distances, the countless stars and galaxies, the fact that our knowledge is always growing, always being refined, it makes you wonder, doesn't it? If the Big Bang Theory is still being updated, if we're constantly discovering new things about planets and stars, what else is out there? What fundamental truths about the universe are still waiting just beyond the reach of our current understanding, waiting for the next observation, the next courageous idea?